Okay, good evening. This is Professor David J. De Los Reyes. Okay, the date for today is October 31, 2023, and the time is around 11:46 a.m. Okay, my topic for this session will be a continuation of my AC machines. It's a long video format discussion. AC machines. We are now on lesson number 51. We are almost done with the concepts and knowledge or study of transformers. So the next time around, maybe I will start discussing alternators. Okay, let's proceed for tonight. The subject matter for tonight will be AC machines, lesson number 51, and the title of the topic is Autotransformer, Power Transform, and Power Conducted. Uh, Under Autotransformer, there are computations which involve equations. So for tonight, I will be bringing out the derivation of the formulas needed in the so-called computation of power transform, and power conducted considering autotransformer. There are equations. Actually, there are two equations in the computation for autotransformer, that is PI meaning is power input. What will be the formula and how to compute for the total power input considering a power transformer. PT is termed as power transform, and what will be the formula and how to compute for the power transform considering an autotransformer. And the third formula is actually power conducted. PC, capital letter PC, or in short it is PC, or in long word it's power conducted or power output. So actually there are three formulas for autotransformer, that is power input, power transform, and power conducted. There are new terms here, power transform and power conducted. Power conducted is similar to power output of the autotransformer, but for this power transform, we'll discuss that one later on. Okay, let's try to bring out the figure of an autotransformer. The complete winding A to C is the primary winding, and the complete winding from B to C is the secondary winding. So this is the load placed on the secondary. The current circulating on the left loop is considered, I mark it as I1. And the current circulating on the second loop and the right loop, the one passing through the load and the secondary part of the autotransformer, I mark it as I2. And the current passing on the windings marked A to B only is only I1. The only current passing through the winding from A to B is just I1. I will need these designations later on in the derivation. And the only current passing through winding from B to C, okay, will be the difference I sub 2 minus I sub 1. I sub 2 will be greater than I sub 1, so the current passing here should be I sub 2, which is going up, minus I sub 1. Okay, so it's the difference. Okay, this is the load RL. The voltage across the secondary part of the autotransformer is V sub 2. The input voltage is V sub 1. Okay, let's try to bring out the derivation. I will try to derive these three formulas here. Power input, there's no problem with power input. Total, the product of voltage and current is actually apparent power, right? So there's no problem with that one. With regards to the conventional transformer, the transformer with the primary and secondary winding, the formula is still the same as this one. But for the power transform, it's a different story. We are now considering what they call this autotransformer. Even the power conducted, it's a different story. So this is new topic, this is new topic, this is an old topic. It's still, what do you call this, used in the conventional transformer, but for auto transformer, it will still be the same. So the new formula here is actually the power transform and the power conducting. Okay, let's try to bring out the derivation. What I would like to prove for tonight is that I would like to prove that this term here should be equal to this. I want to prove this one, that the product of the number of turns on this portion AB times the current passing through it is equal to the number of turns on the winding from B to C, okay, times the difference in current I2 minus I1. I want to prove this one because if I could bring out this one, okay, we'll bring out this one. And if we could bring out this one, what you call this, we derive first this one, right? So after deriving this one, that this one is equal to this, we'll conclude that from this, it should be this equation here. And from this equation, okay, we could now bring out the formula on how to compute for the power transfer. Okay, so we'll pass by this long process per se. Okay, it is something like this. Ratio of transformation is actually B1 over B2. For this transformer, the ratio of transformation will be the ratio of the input voltage divided by the output voltage, okay? Or the other equivalent of ratio transformation from the definition of ratio transformation from the conventional transformer. It should be the number of turns on the side BC or winding BC, okay, divided by the number of turns on the total number of turns AC. This is standard for conventional transformer, the transformer with the primary and secondary winding, and so with auto transformer. So we could still use this one. It should be B1 over B2. Of course, B1 is greater than B2, so A will be a step down, right? So if it is a step down, of course, the total number of turns on the secondary will be greater than the number of turns on the primary, right? So it will be this one. If the efficiency is 100%, assuming there will be no core loss, we will place the product of B1 I1 should be equal to the product of B2 I2. The product of voltage and current is actually apparent power. Apparent power is actually BA. Number 1 should be equal to BA. Number 2, this should be equal if the efficiency of the transformer is 100%. That's according to this, right? Let's now try to work out on the secondary side, on this portion here. On this portion. Ampere turns subscript secondary, okay? It will be the total number of turns on the secondary, right? Times the current passing through the secondary winding only. The total number of turns considering point B and C is just capital letter N with the subscript BC. And the current passing through it is actually I sub 2 minus I sub 1. Right? So if I will try to, okay, I will try to take the equivalent of NBC. NBC, number of turns on BC, should be the total number of turns on AC minus the total number of turns considering point A and B. So this is now NAC, the total number of turns here minus this is actually equal to this, right? This one here is the difference of the big one minus the small one. Okay, it's just the difference. No problem with that. For the product, it is multiplied by I sub 2 minus I sub 1. Oh, this is just algebra. Expanding this one, there will be 4 terms, right? This should be the first term, second term, third term, and fourth term. This one here is just the expansion of this. We distribute it, right? But the other definition, we call this equation number 1. The other definition of ratio transformation in terms of number of turns in current is this one. Okay? This is the other equivalent of ratio transformation. The first equivalent is actually this one in terms of voltage and number of turns. But in terms of current, it should be this one. So considering this circuit here, the ratio transformation should be NEC, the total number of turns from A to C. Okay? Divided by the total number of turns from B to C should be equal to this current here should be I sub 2. This one here should correspond to this. Okay, the current passing through NBC will be I sub 2, and the current passing through NAC should be I sub 1, and this should be equal to A. Or we could remove this one now. And if we try to compute for I sub 1, we put I sub 1 over here, or it's just like this. This is just algebra. We'll try to compute for I sub 1, right? So we will multiply this one by I sub 1 times the reciprocal of this, NBC over NAC. Right? So the left hand side multiplied by this NBC will cancel out. This NAC will cancel out. Okay, what remains on the left will be I1. For the right hand side, it will now be, what will come out? We will multiply I2 over I1 times this. So this I1 here cancel with this, right? So this one will remain, this one will remain. So it will be NBC over NAC times I sub 2. So in terms of I sub 1, in terms of I sub 2, will be the number of turns on the point BC and number of turns on the point EC times I sub 2. We substitute it to equation number 1. This one here, we put it on equation number 1. This is just algebra. I don't have. So NEC I2, NAB I2, okay. This is NEC. Then we replace this I sub 1 here, this I sub 1 by this value, right? The one we computed, NBC over NAC times I sub 2 plus NABI1, okay? But if we try to multiply this one, this NAC, NBC here, or NAC, cancel out. So if we try to expand again this one, am I still on camera? NAC I2 minus NABI2, okay? This one will be minus NBCI2 plus NABI1. Then I will try to combine this one here, this is with an I2, right? So this is I2. The first term will be NAC minus NBC. So we are done with this one, right? Minus NAB, NAB. Where is NAB? NAB, common factor, okay? The first one should be plus, because the product of minus NAB times I2 is this one. So the first one should be I sub 2. And the product of minus NAB times minus I sub 1 is this one. So the inside will be minus I sub 1 close quantity. Right? I just combined this one here, NAB. The common term is NAB. And again, if we try to expand, this should be I2 NAB. But this NEC minus NBC, the difference NEC minus NBC is actually NAB. So I replace this one, this difference here by NAB. So this will now by I2 NAB. We try to simplify this one minus NAB I2. A minus and a minus will be plus NAB I1. And luckily, this is plus, this minus, they are both similar, so they cancel out. Right? So what remains? The right hand side will be equal to NAB I sub 1. And we will equate now this one. We have proven that the ampere turns product number of turns on the terminal AB times I1 should be equal to the number of turns on the BC times the current passing through I2. Why did I equate this one? It is like something like this. The total number of turns here times the current passing here. We have proven that it is actually NAB I1, right? And this is we equate this to this one, right? So NAB I1, the product of the number of turns on the part AB times I1 should be equal to NBC I2. This was the original thing, right? We have proven that the number of turns and times the current passing here should be equal to the number of turns here times the current passing here. That's why we came out with this one. Right? And from this, from the foregoing analysis indicates that the power transform should be, in terms of voltage and current now, the first one should be B1 minus B2 times I1. The difference B1 minus B2 is actually the voltage across this, times the current passing here is I1. Okay? And the voltage across this is actually B2. Okay? And the current passing here is actually I sub 2 minus I sub 1. That's why, again, we brought up this one. And this one emanates from this. Okay? Okay, let's now try to compute for the power transform using any of these equations will be fine. So, but we will be using the first one. Okay? Before we will try to simplify this one in terms of the other values, we will let A to be equal to B1 over B2. For this transformer, the ratio transformation is the ratio B1 over B2. So if we compute for B2, it will be B1 over A. Right? So going back to this, instead of writing the complete word power transform, we'll just simplify it as simply PT, meaning power transform, and this should be equal to, I'm following this. It should be I sub 1, right? Minus B sub 1 inside. And what is B sub 2 inside? B sub 2 in terms of B sub 1 is actually B sub 1 over A. So this is B sub 1 over A. Common factor B1 inside, we could bring it out. So this will now be I1. Common factor, right? B1. What remains inside will be just be simply 1. Okay? Minus 1 over A. But what is the product of I1 B1? Product of I1 B1 is actually the power input. The total power input on the autotransformer. So we will just represent this product I1 B1 by capital letter P with the P and I, meaning total power input. Okay? We simplify this one. Power input is just simply capital letter P and I. So power transform now will be the product I1 B1, which is power input times the quantity 1 minus 1 over A. So for an autotransformer, the formula on how to compute for the power transform is actually, it should be the power input times the quantity 1 minus 1 over A. Okay? And this should be in watts or voltampere. If there is a K, it should be kilowatts. If there is a K, this should be kVA. That is the power transform considering an autotransformer. So for a power transformer, if you want to compute for the power transform, it should be the total power input times the quantity 1 minus 1 over A in terms of kilowatts or kVA. Okay? Okay, let's try to bring out another term. Capital letter P and C, meaning power conducted. Power conducted seems just like the power output of the secondary conducted. Why conducted? Because the power output is not actually what you call this taken by using an induction process, right? Because there is no secondary winding. It's just the whole windings are both primary and secondary. Unlike in the conventional transformer, there is the primary winding and secondary winding. So if we try to bring out the term, the output on the secondary, it would just be simply the conventional power output. But under autotransformer, the power output is termed to as power conducted. Okay? it was brought out or bring out, it's not through induction, it's just conduction, right? So power conducted will be, it's just like a power output is power input minus, it's not losses, right? Power conducted will be power input minus power transform, right? So this should be power input is B1 I1. Power transform is actually, what is power transform? It is this one. Instead of placing PI, since there is a B1 I1 here, we will just go back to the original definition of power input. B1 I1 times 1 minus 1 over A. And if we try to expand this one, it should be B1 I1. This is a minus and a plus, this will not be minus. A minus and minus will be plus. But luckily, this is B1 I1 plus, this is minus B1 I1. They're similar, they cancel out. Right? So what remains for the power conducted or power output considering an autotransformer? It is just simply, there is an A at the bottom, right? So I will simplify it, 1 over A, and the product B1 I1 is power input. So the power conducted or power output of an autotransformer will be the power input divided by the ratio of transformation. Okay, it's either kilowatts or kVA. Power conducted, considering an autotransformer, is same as output. So the needed formulas on how to bring out the power input considering an autotransformer will be the product B1 I1. Okay, power input will be the product of the input voltage and the current entering. And the power transform will be the power input times the quantity 1 minus 1 over A. It come out like this from our derivation, right? So don't ask me why there is a quantity 1 minus 1 over A. We derive it. It comes from this. Right? And for the power conducted, it should be power input minus power transform. And after simplifying this one, power conducted or power output for auto transformer will just be simply 1 over A times the total power input, and the unit of this should be kilowatts or kVA. I think guys, these are just the needed formulas under the concept of what they call this auto transformer. Okay, so just in case you'll be solving problems involving auto transformer, these are the needed formulas. Power input will be B1 I1. Power transform will be the product power input times the quantity 1 minus 1 over A plus quantity. And the power conducted or power output will just be simply 1 over A times the total power input. Okay, good evening or good morning again. Now, good morning from Los Angeles. Professor David Jennifer.